Okay, so the crust of the Earth. You ever wonder why they call it the crust of the Earth? It's crusty about it. Are we a pizza floating in space? Not exactly, but it is a fairly good description because when this crust of the Earth originated, you know, like maybe 4 billion or so years ago, theoretically, it happened when the Earth was impacted by a comet, most likely, and comets are mostly made out of water, and that's where we got our water from. That's one theory. There's other theories about where we got so much water and why we got more than other places in the solar system. But as you are aware, water is a very good cooler, or coolant, and so consequently all that heat, because before this the Earth, like the rest of the inner planets, was just kind of a molten glob, still hot from its genesis from the sun. It's that water then, of course, would evaporate rapidly, condense up in the upper atmosphere, come back down, and you basically had a constant rain cycle of some estimate about 200,000 to 500,000 years long. And in that process, as it would go up in the atmosphere and condense and come back and radiate heat out from it when that happened, about half of it would go back out into space. So eventually it cooled things down enough and cooled that molten layer underneath down enough that that layer solidified, yet still leaving kind of a melted layer underneath, kind of like a crust, right, on the top of it. Like fried ice cream. You remember fried ice cream? Oh yeah, fried ice cream. Well, they take ice cream and they roll it in some kind of breading, crunchy kind of stuff, and then they fry it real quickly. Not too long, of course, but they fry it enough to get that outer part to crust up, and then the part underneath is still solid, kind of melty liquid, and you bite into it. It's amazing. But similar idea in that the crust of the Earth is a hard shell underneath a more or less liquid layer that's underneath it. A layer of magma known as the Lithosphere. Who put that?
Me too.
You know what? I'm going to give you a technicality point there because technically it is molten rock.
Exactly.
But we call it magma. Magma.
Really?
Okay? And so as you might imagine, this layer of solid rock on top of a layer of melted rock, it's not going to be able to like hold it. It's going to break, in other words. And although the rest of the inner planets in our solar system cooled off a long time ago and their crust solidified, on Earth we have something else unique about the planet in that we have a large amount of uranium in the mantle of the Earth. And uranium, of course, is radioactive. So it's giving off heat constantly, and that heat is enough that the top part of the mantle is melted. It's magma. And the bottom part of the crust being in contact with that is also melted. So that melted layer between the crust and the mantle is known as the asthenosphere. And it's constantly heating, it's constantly receiving energy, it's moving, it's basically boiling around underneath, convection, currents, and all that. So like I said, as you might imagine, you're not going to have one continuous solid piece of crust that exists around the Earth. It's fractured and fragmented into about 20 different plates. Okay? The reason why it's approximately, some of them are fusing together, some of them are a little fractured, some people classify those as more than one, etc. So the generally accepted figure is about 20. Okay? Now another factor of this, or this event of the original cooling of the crust, was that some of the crust of the Earth was more dense, made up of more basalt, basically, but its material was such that it was more dense than other plates of these plates, and those that were dense sunk down lower into the asthenosphere, and they're also thinner, and those make up our ocean plates, or oceanic plates. The ones that became land were less dense, lighter, and thicker, and those are what are known as our continental plates. Those are the land plates. Okay? So that's important when we look at the way these interact with each other. And it's also important, of course, because we have both aquatic environments, we have the ocean, and we also have land environments as well. So just one more thing to make things interesting here on Earth. Okay. So it is where these plates interact with each other that we have a number of different occurrences. So like I said, you need to know not only what's going on, we just described what plate tectonics is, the movement of these plates around. You need to know what's going on at the boundaries of these things. Some examples of those are given here. So for example, you have divergent. So when we look at divergent plate boundaries, that is moving apart, spreading apart. So as you might imagine, when that happens, you have magma that's underneath coming up, boiling over the edges and piling up on the sides. So we ended up with a valley where the actual plate, where the actual plates are spreading apart. And then on each side of that valley, you have relatively short mountain ranges. Mountains 4,000, 5,000, 6,000 feet tall that pile up on the edges because that magma just kind of oozes out and piles up on the edges of it there. Sometimes it'll pile up high and reach the surface, like an area along the mid-Atlantic ridge in the North Sea. There's a volcanic island. Any ideas what island I'm talking about there? North Atlantic, volcanic island.
Ireland.
Not Ireland.
Greenland.
But it's a good guess. Not Greenland also a good guess.
Iceland.
Iceland, yes. Iceland's a volcanic island. That's why, because it is on the mid-Atlantic ridge, and that's where the magma has come up and solidified and hardened. It is still coming up and flowing out right there. So that's the mid-Atlantic or mid-ocean ridges. It's one of the mid-ocean ridges. Okay. Most of them are in the ocean, by the way. The Atlantic and the Indian Ocean is where you find these divergent plate boundaries now. There are some on land, or at least one in particular being the African Rift Valley. And you can see where the African Rift Valley goes up. You can't really see it so much from the map, but you can see where it goes up. That's what causes the Red Sea there, is that division there going up along the east coast of Africa, splitting apart in that area. Kilimanjaro was produced by this, and you have a number of both lakes and volcanoes and stuff that occur along that area, the African Rift Valley. But most of them are underwater where this occurs. So that's one type of plate boundary. And pretty much the same thing's happening there. As like I said, plates are spreading apart, magma is piling up on the edges. I'll let you look at a picture of that in a minute. Also, though, you have convergent plate boundaries. Okay? So I want to make sure you differentiate between the two, because when we get to convergent, there's three different categories of that. So your convergent plate boundaries, the things that happen to those are going to be dependent upon what kind of plates are coming together. So you got two types of plates, oceanic and continental, right? Oceanic, continental. So there's three different ways in which those can interact when they come together, or the three different combinations, I should say. You can have ocean to ocean, okay? This happens a lot in the Pacific Ocean. The Pacific Ocean is basically getting squeezed on all sides. It's shrinking. So you have that. That has produced most of your South Pacific islands in the form of volcanic island arcs. And in this case, you've got plates pushing together. So they're going to push up kind of tall enough to breach the surface of the water. And they form these real slender, steep-sided volcanoes called shield volcanoes. And that's why you see that particular type of formation in the Pacific. And that's one example of what happens when you have an ocean-to-ocean convergence taking place there. Then you have another type, which is when you have an ocean and continental plates coming together. Now in this particular case, remember that the continental plates are lighter, less dense than the oceanic plates, so that means the oceanic plates tend to get pushed underneath the continental plates. And that's what we call, when one plate goes underneath another one, we call that subduction. So make sure you know that term, put it in your notes. Subduction. Okay, so I'll show you the diagrams as well. So sub going underneath. So when this happens, you have on the land side, you tend to form volcanic mountains as the crust is being pushed up and the magma that's forming underneath it pushes up through it as well. Sorry about not giving you enough space there. Mountains. And on the ocean side, as that plate, that ocean plate is getting pushed down underneath, you get deep ocean trenches. This is where we find the deepest parts of the globe. The Marianas Trench, the Puerto Rican Trench. So that is because of those plates being pushed down and pushed underneath the continental plates on that side. Okay. So what we see is what is happening, as I just mentioned, is in the Atlantic Ocean, you've got a lot of divergence going on. You've got the plates spreading apart. The Atlantic Ocean is actually getting bigger. So it's moved apart, and therefore North and South America are moving towards Asia and Australia. So this over here is pushing together. The Pacific Ocean is actually getting smaller then. And all along the edge of that, you have the continental plates of North and South America and Asia and Europe pushing into the Pacific Oceanic plates. Yeah, Chris?
Isn't like California and Washington and Oregon, are they going to separate eventually?
Well, you've also got, you've got what we would call transform plate boundary there, where that whole part, that the California Peninsula and everything is pushing up towards there. Theoretically, it may one day push off into the ocean. It'll be millions of years before that happens. But yes, that is part of what we're talking about. And actually, we're going to talk about the transform type in a minute.
Yeah.
So that whole area around the Pacific, you have a lot of earthquake activity. You have a lot of volcanoes along there. That's why it is called oftentimes the Ring of Fire. Okay, it's also a Johnny Cash song. Also bad case hemorrhoids. But so that's kind of, there's a lot going on in that particular one. And as we shall see, this is actually where the crust is getting recycled. Okay. So we got convergent ocean to ocean, convergent ocean to continental, and then that leaves us with continental to continental.
There we go.
Okay. And I saw this on I-4 the other day. Two of them ran right into each other, two continentals. Lincoln continentals. But when this happens, both the plates are thick, they're less dense, they're at uneven levels, so whenever you have that happening, just like when the ocean came together, they push upwards, this is going to happen too. It's going to produce very tall mountain ranges and very broad mountain ranges. Not very volcanic. You do have some areas where you get volcanoes there, but you got a lot of crust there between the magma and the surface. So when it piles up there, and it really just kind of warps and pushes together. It's like taking a blanket on a bed and pushing the edges of it together. You form those curves and stuff, and you get these broad, very tall mountain ranges that form when that happens. Okay. The Himalayas is an example of that, as the Indian subcontinent is moving into the Asian continent. So that's a continent-to-continent convergence there. So that's what happens to those. But not all of them are linear, moving back together, moving apart. Some of them are rotating and sliding past each other. So there's no set rules about the way these crustal plates move. And those areas where they're sliding past each other, are called transform boundaries. Yeah, that's true. False is true, but that's not what we're looking for. But I'll go ahead and give you a point for that. Example, San Andreas Fault. Kind of a cheap point, but whatever. So what happens is that they're kind of rotating past each other. So when that's happening, now these plates move at about 3 to 7 centimeters a year. So it's not, you're not like, whoa, hold on, the continent's moving. But they are of course huge and massive, and therefore they deliver a lot of energy when they do this. Okay? So under normal conditions, they just kind of move past each other slowly, which everything's fine. But every once in a while, they'll get stuck. Okay? And then when they get stuck, that energy gets built up, and eventually it slips and continues sliding. So when that slippage occurs, what do we call that? That is an earthquake. Bless you. Sliding past each other, earthquakes tend to occur in those areas when they get stuck. By the way, you also have earthquakes where you have subduction, because that's the place you're sliding against each other. They tend to be much deeper, though, and not as destructive, although they're more widespread. It's also where tsunamis come from, is when you have a deep focus earthquake and the ocean one slips down. So these are your different ways in which the plates can interact with each other, but that doesn't mean that that's the only place you're going to get things like mountains and volcanoes. Every once in a while you get what we call hot spots, which is a geological formation or volcano where the crust not near the edge of the plate, of one of the plates, but near the interior of it is either thinner or there's a crack there or whatever, and the magma pushes up through it, forming a volcano. Yellowstone is an example of this, and the Hawaiian Islands are an example of a hot spot. Actually, the hot spot is moving, so that chain of Hawaiian Islands is in order of age. As that spot moves, it pushes up a new island in each area. They've actually got one that surfaced in the 1950s, I believe, that's near the end of the chain, and of course you've got the other larger ones that have been there for a while. So that's a summary of your different types of geological formations and things that happen due to the interaction of plates. All right, so this leads us to a cycle, probably the longest cycle that you'll find in science, at least as far as earth science goes. And that is where the crust recycles itself. Okay. It goes through three different stages as far as the type of rock. It's not crucially important that you know those things. They don't really have an impact on living organisms so much, but you do need to know the three different types and what part they represent in the whole cycle, kind of thing. If you wanted a starting point, it would probably be where magma or lava solidifies. So it could be either one. Group 8, you went first, which you put the lava. Magma is actually a better answer. But since Group 8, you put yours up there first, I'm going to give you both a point. But magma will solidify, and I think it's a better answer here also because most of this happens underground. It's what we call intrusive igneous rock formation. Okay, and all that means is that the plates come together, they push together, and that leaves a pocket in there, and so the magma comes up and fills it in, right? And so a lot of it, the interior of your mountains and things like that are basically made out of this magma that's come up and solidified and cooled inside there. That's what we call intrusive igneous rock. Sometimes it does come out as lava. It breaches the surface and comes over the side. That would be extrusive. But either way, they're going to cause formation of crust and land, and particularly in geological features that we call mountains and volcanoes. Okay. So then from there, you have the process of erosion, okay, and weathering and erosion, I should say. So wind and water will break apart these pieces of rock, and then gravity's gonna bring them down. The weathering is the actual fragmentation of it, and then the transport of it is erosion. Okay, but basically you're breaking apart those bits of igneous rock that came up, that formed your mountains, etc., and gravity's pulling them down, and they're going to end up going down into your river valleys and eventually onto the continental shelf primarily. Eventually they'll go to the ocean floor. Okay. So as these sediments year after year from the wearing of the water cycle and everything and the wind break apart, settle down, move down in layer upon layer, eventually many of them will compress into a type of sedimentary rock. So the sediments become sedimentary rock just from that pressure, etc. And then depending on where this happens, where they finally settle down, whether it was on the continental shelf or maybe even in the ocean floor, whether it's near a convergent plate boundary or if it settles out in a river valley near to the middle of a continent, they will either go relatively quickly, which in geological terms is like 1 million years or so, into, get subducted, but pushed back into the asthenosphere where they can start the whole process again. It's right here. Or they will stay buried for a while before they move out towards the edge of the plate. And if that happens, a lot of times the pressure and the heat will cause them to chemically transform. They'll become metamorphic rock. Metamorphosis means to change. Metamorphic rock is just chemically changed into a different substance. Eventually, most of that is going to end up, even the metamorphic rock, being pushed back down in the asthenosphere. And that means you go back to magma, of course, and that starts the whole process again. Okay? All that together is known as a rock cycle. And I've got a diagram, of course, show you that more diagrammatically speaking, but those are the processes and the steps there. So what? Why is this important to life? That's our second thing to look at here. Describe the importance of the rock cycle to life. Here it is right here. Soil nutrients. And I think I said at the beginning of the year when we were going out and we collected a couple soil samples, if one of the things I'd like for my students to come out of this class with is a very deep appreciation of dirt. Because it is crucial, second only to water. It's crucial in the ecosystem. And not only the physical components of dirt and everything, but that the dirt has minerals in it. And because of this rock cycle process, because of the fact that new mountains and landforms and everything are still being created, which can break apart and come down and fertilize the valleys and things like that, which by the way is why a lot of civilizations started there in the river valleys, because they're very fertile because of those sediments and stuff. But those nutrients being able to be spread out in that way from the crust of the earth, that the soils remain fertile of a lot of different minerals that they get, and life continues on. Bless you. So that's one thing that is a very good reason for a reason why we should appreciate this whole rock cycle, lithosphere, volcanoes, all that kind of stuff, the natural disasters that actually help us to be able to eat. But the other thing is that if we didn't have the active crust with the magma underneath and the plates continually pushing into each other and pushing up volcanoes and mountains and stuff like that, would we have any land left? Because what's happening on this end? Right here. It's breaking down all these mountains, right? It's wearing them down, constantly erosion. The Appalachian Mountains used to be 30-something thousand feet tall. Now they're about 6,000 feet tall. So theoretically, as long as we had water and wind and air in the atmosphere, if we didn't have this active crust of volcanoes and those kind of things continually pushing up new mountains and providing more land, then everything would have worn off into the ocean. You could easily take all the mountains on Earth and shove them into the ocean and you have room to spare. So we would no longer have any land left. So that's another good thing there for a reason why we can appreciate the fact that ours is the only planet to have this. So there you have it. There's within one statement, that's the main thing that this active crust of the lithosphere helps life on Earth, is the fact that it continues to provide nutrients for the things. All right. So this particular bullet is a little bit off the subject because it's not really about the lithosphere. The lithosphere is a crust of the Earth. This is more about the interior of the Earth, but it is important to understand because there's one particular property here of the Earth, another property, unique property that protects us, and it is also something they have asked on the national exam before about the core of the Earth, so we'll cover that now. Going down for the crust through the asthenosphere, the next layer is the thickest layer, and it is actually the majority of the Earth is what we call the mantle. And it's rock, but it is constantly heated both from uranium and from heat from the inner core, and to the point where it's actually flowing. They have shown that there is what they call high viscosity flowing. So in other words, it's moving very, very slowly, but the rock itself is actually flowing. If you looked at it, it would look like a piece of rock. As a matter of fact, there's some areas in the world where the mantle extrudes above the surface, and you can actually see it. It looks like rock. But it is actually moving and everything because of the heat that's being produced. Like I said, very rich in uranium, among other things, mainly silicon, oxygen, aluminum, like we saw on the first slide. Because that's what the crust is. It's a mantle that's been melted and then reformed there. So you have that through however many miles, I don't know, deep. And then you hit the liquid outer core, which is mostly iron, with a little bit of nickel in it. So we have an iron-nickel outer core, and then we have a solid iron-nickel inner core. So that's cool, right? Got that? Good thing we have that, right? It actually is a very good thing. That gives us a magnetic field, the spinning of the iron core, of the solid core within the liquid of the inner core. You know, the dynamics of electrons, all that kind of stuff. Anyway, it makes the Earth have a magnetic field around it. And that protects us from some of the really high energy, really nasty kind of radiation from the sun, like gamma rays, X-rays, cosmic rays. Most of that is deflected by the magnetic field. Now here's the creepy thing. That field switches back and forth. It does so on a fairly regular basis. Scientists are not sure why, nor are they sure what happens when it does switch back and forth. I don't know what the time period is, or if they have a cyclic time period. Somebody can probably look that up, etc. But that field, north becomes south and south becomes north again periodically. We've seen that through history. They can tell that by looking at the magnetism of the layers of crust as they formed on the ocean floor, and it's flipped back and forth over the years. So that could happen, you know. Let's hope that it doesn't open up a window of high energy radiation along the Earth as it moves. Who knows? But if you've seen the movie The Core, that's that's based upon the core actually stopping and with us no longer having this magnetic field. But it definitely does serve a purpose of protecting us from high energy radiation. I've got to do that D again. That's just nasty. This is why I usually write in caps. Radiation. Radioactive. Alright, so one final thing for note close at home. Not all of the bedrock that we have around the world is made up of the crust of the Earth, of the non-living geological rock kind of thing. A lot of areas, like Florida, good old home. France is another one that's an example of this. The substrate is made from ancient coral reefs. It's actually biological in origin. And there remains. And that mineral that you find in there is mainly calcium carbonate. It's the primary component that you find in this type of geology. Now, as most of you know, one of the things we obtain from the crust of the Earth, the use of the lithosphere as a resource, is metals. So that's what most people think of when they think of mining, although it's a small part of that market, as a matter of fact. But this is what people have been using the lithosphere for a long time. And one of the things I want to impress upon you is that most metals are not present in the crust in their metallic form, in their elemental form. In other words, you don't dig down and find a chunk of aluminum sitting there, or a vein of iron, or sometimes you might find copper. About the only metal that is found in its native elemental state is gold. And that's one of the reasons gold is, you've got gold artifacts that have been around for thousands of years. And one of the reasons why it was first discovered and used is because it being non-reactive, you can dig down and there'll be gold there. It'll be like a vein of gold or parts of gold and stuff like that. And you can melt it out pretty easily as well. The other things are chemically combined with other things, and they're found in minerals or rocks, what's commonly known as an ore. O-R-E. So that's a rock that contains a metal that you're trying to obtain. Now this is important when we look down here, because part of the impact of mining these metal ores and things is the amount of energy that goes into refining them, and the amount of energy and use of hazardous substance that goes into taking it from being a rock into being an actual metal. That's why that thing's messed up. So there are other things as well that are not metals that we dig up out of the ground, including clay, salt, limestone. And limestone's big in Florida. Florida is a mining state, believe it or not. Although we're going to keep that point, but when we take the limestone out, sometimes we use it just as limestone, but a lot of times they extract phosphorus from it. And phosphorus is useful for fertilizers, industrial type detergents, things like that. Marble, granite, those are some of the other things that are dug up out of the ground. And all of your fossil fuels are considered to be mineral resources, phosphorus. All of your fossil fuels are mineral resources. Okay? So in geological terms, if you dig it up, or resource terms, you dig it up out of the ground, it's considered, it's a mineral resource. The primary way in which that is done, most of the time, is through surface or strip mining. You go to the place where you think it has that mineral that you want, and you start digging from the surface down. Oftentimes using explosives. And it is a very destructive process. You get complete destruction of the habitat in that area and all the things that come along with that, which we'll talk about here in a minute. But it's the most common type. I tell you this because, like I said, it is a very environmentally destructive one. But most people, when they think of mining, they think of subsurface mines with mine shafts and the cars on the trolleys and all that kind of stuff. That's more rare. They don't do that as much as they do strip mining. And it is more expensive and more dangerous than typical strip mining. Okay. And then we also mine stuff that's underwater, or in aquatic areas. I'll take wet. But we dredge stuff particularly off of the continental shelf because a lot of minerals and things have accumulated there. Aquatic. Okay. So different ways in which we mine and different stuff that we mine for. What does it do? Mining is one of the most environmentally impactful human activities. Okay. Complete habitat destruction where it happens. You're not going to have a little preserved pond or forest area in your mining area. When you're going to basically wipe out everything that's there at ground level when you do this. Okay. Along with that always comes soil erosion. Whenever you're clearing out plants, vegetation, etc., you're going to have soil erosion. So there's soil loss there, and that erosion then becomes either air or water pollution. And the water that's polluted is both the surface water and groundwater, because of course when you're digging down in the mine, you're getting down in the groundwater as well. And if you're digging out toxic substances like lead and mercury and cadmium and those other types of heavy metals that we know are toxic, that's going to get in the groundwater, it's going to run off into the surface water, it's going to be in the dust that's in the air as a type of air pollution, or just the dust itself. So those are all the many pollution impacts that we have from mining. And then there's something called acid mine drainage, because whether or not you end up bringing up some of these other things like lead and mercury to the surface, it's pretty much a variable. You're going to bring sulfur to the surface. Sulfur is very common in the crust of the earth. And sulfur, when it's exposed, gets eaten by bacteria, and those bacteria give off acids. And then that acid rain, or the runoff that comes from there being acidic in nature, also will dissolve those toxic minerals and other kinds of things in the soil more when it takes it off. And so that acid rain off, that acid mine drainage, is not only acidic, a lot of times it's filled with these toxic metal ions. It's a source of acid shock in a lot of cases. So most areas where you have mining taking place, there's water contamination as well as air contamination all over the place in those areas. Okay. And so there's some more environmental impacts. So you have the whole habitat destruction that happens there at the site because it's happening, and then you have the air and water pollution that's also produced there where it happens. And then once you get that stuff out of the ground, you've got to process it. So the processing, particularly of metals, uses a lot of energy. And a a lot of times poisonous chemicals, like hydrogen cyanide is used in gold and silver refinement. And although we've got a pretty good handle in the industrialized world on keeping those substances out of the environment, in a lot of developing nations they don't regulate as much. As a matter of fact, in some Amazon areas there's this practice where people are going out and actually processing the gold and silver right there on the riverbank. That's actually pretty easy to do chemically. But then, of course, they're just dumping all this toxic stuff right out there in the environment and moving on, taking their gold and silver with them. So that's, you know, whatever we have some amount of regulation on here in the developed world, a lot of times in developing nations, you don't have that. So you have pollution from that taking place. Mineral resources, those things you get out of the ground, are all, I'll take limited. The technical term we're going to use for that is non-renewable. All right, so far, to illustrate the difference, so far we have talked mainly about the resource of water. Okay, we talked about the atmosphere. We said, yeah, atmosphere is kind of a resource, but it doesn't really run short. But water is what's known as a renewable resource. And it's a renewable resource because fresh water, actually, is what we're talking about as far as a resource go. Fresh water gets renewed, purified by the water cycle. And so as long as you use that water at a rate that is less than the rate at which it's being replenished, the fresh water, by the water cycle, by precipitation, you'll always have a good fresh water supply, right? It's like a bank account, okay? So that's a property of renewable resources. We'll also look at biological renewable resources like trees and fish pretty soon. But mineral resources don't do that. They are not renewed in a practical time period. Now you could say fossil fuels, eventually we'll have more fossil fuels from the dead organisms we have now, but that's not a practical time period. So they're not renewed on a practical timeline, so that means that once you've used up what you have, you're going to have to go somewhere else to get it. Okay? So this is a practical problem, of course, because of the supply, and it gets less and less, and every time you have to dig another mine, that material gets more and more expensive and more scarce. And then it's a problem from an environmental perspective because that means you're going to have to dig a new mine. And so you've got continual environmental impact all over the place as we keep using up the source of these minerals through our practices. Okay. So what can you do? Final thing here, cures. Okay, that's our final level of understanding of this. As far as mining goes, it's pretty difficult to really make it where it's not a very destructive process. It's just the nature of when you're digging massive amounts of rocks and everything out of the ground, you're going to have all these different things. Okay. So when you have that problem of a process that's not, it's very difficult, if not impossible, to make it better, then you want to do less of it. So the way to do less mining is to use less of those raw materials, which means reducing, reusing, and recycling. Okay, so that is really the main reason why recycling is particularly important with metals and plastics, is because they're a non-renewable resource. And therefore, to make those same substances out of new materials, not only do you have impact from the mining of all these, and your oil and natural gas, certainly you have oil leaks and stuff like that, but also the refinement of these substances is usually more energy intensive and may use more toxic chemicals than the recycling of it. So that's why it's particularly important to use those ones. You can also use alternative materials, typically ones that are renewable, like using wood fibers or other types of biologically grown materials to replace those that are not renewable. And also, of course, finally, with the mines, once a mine is used up, it's required, at least in the United States and many industrialized countries, it is required that they restore that mining area back to, as close as possible, back to its original state. But once again, we do that here, but there's many places around the world where they do not. And as you can also imagine, that's a very expensive process. And you know, going in, if you're going to dig a mine, you know eventually you're going to have to fill it back in. So what do you think mining companies do as far as where they're going to mine? Where do they end up going to mine?
Places where they're not regulated.
Exactly, places where there's not so many regulations. So sometimes you can displace an environmental problem, but until you reduce the usage in the first place, you're not going to solve it. Questions? Anybody?